So there's one more point of claimed difference between the two methods. First of all, we said certainty, deduction, collecting data, abstraction, using logical rigor, aiming for general case or specific case theorems. Turns out all of these things, when you particularly take care in the understanding the meaning of these claims and then checking out whether they check out or not, turns out that they don't. It's not the case. The final point I would like to talk about is another point that also Feynman raised in that clip, which is that mathematics considers any hypothetical situation at all, only limited by imagination, which is kind of what we're talking about here and there in the discussion that we had earlier. And then physics, on the other hand, only cares about one world, just one world, one specific world only, which is the objective, real physical world that we exist in and experience. So science believes this physical world exists. Science believes it has access to it. And these assumptions we're going to talk about later, of course, when we tackle more directly the contents of the scientific method, because you can't open a physics books and read those. They don't. It's not like it's the front page. It should be, if you ask me, but it's not. So it's worthwhile discussing them. That world, that one physical world that we all live in and we have access to and we can understand, is the world that physics is concerned about, not any other world, just that specific world. Not many worlds, not infinitely many like in mathematics. Mathematics is not concerned. You can construct whatever fictional, imaginary world you want to think of. Kind of entails some Platonic kind of ideas, but whatever, this is not our discussion for today. Let's see if this checks out. I have this example here on slide 15. A mathematician and a physicist, two people, they try to discover the length of the hypotenuse, so the biggest side of this triangular field. It's a real piece of land. It's out there in the real physical world that we can go and measure. So what does the physicist do? Because he does not care about all the imaginary different worlds. The physicist goes, takes a measuring tape, the most precise one we have, right? The most precise measurement tool. You want to take a laser, you want to take a surveying tool, whatever, for simplicity, right? Imagine this. And then goes on measuring the first side A. Turns out it's between 0.9 and 1.1. Of course, there is an error because he's measuring with, a physical object. And whatever this physical object it has, those properties, it kind of dilutes, it's kind of with temperature, there's errors in measurement that you can think of, and probably people who are more specialized than me in physics can tell us all about these different kinds of errors that physicists are well trained to measure and quantify. So there's an error in this measurement. Arbitrary, right? Imagine with me, it could be more specific, less specific. For simplicity, I took between 0.9 and 1.1, okay? Whatever unit you want, meters, kilometers, whatever. B as well, same thing. And then you measure C, and it's between 1.3 and 1.5. This is the result that the physicist got. And then he goes to the mathematician. He's like, this is what I got. And then the mathematician had a different thing going on, because the mathematician is thinking of imaginary, abstract, right? Infinitely many worlds. The mathematician takes the measurements that the physicist has done for sides A and B. Because there is no data, the mathematician has to have some data. He can't start, or she can't start working on the problem with zero information. In mathematics, we all know that you have to give us the given, give us the axioms, give us the hypothesis, give us something that we can use. So he takes the measurements that the physicist has made, and whichever method the physicist is happy with. A is between 0.9 and 1.1, B the same way. And what does the mathematician do? He uses Pythagoras' theorem to calculate a lower bound for the side C and a higher bound for the side C, which happens to be, in this case, if you do the math, between 1.27 and 1.56. If you do the rounding, you will have very, very similar results to what the physicist got by direct measurement of the real, actual, 100% flesh and blood, one universe that we live in. The question is, which one of those two is only concerned about one possible unique world, and which one is concerned about infinitely many? This is the real question. Because if you were going to accuse the mathematician of being concerned about infinitely many worlds and infinitely many possibilities, I will remind you that those errors that the mathematician had, those errors were due to the physicist's errors in his measurement. If you had given the mathematician A equal 1 and B equal 1, the only answer that the mathematician would have got was the square root of 2. The one unique answer and the one unique situation that we have here in the unique world of Euclidean geometry is the square root of 2. That's only one answer, one specific world where this is the case. Whereas in the physicist world, this could be anything between 1.3 or 1.5. Exactly how many? Infinitely many. Uncountably infinitely many, not only infinitely many. So can I keep accusing the mathematician of not caring about so only caring about imaginary worlds, and the physicist caring about this is a situation where originally the way I wrote this example was the following. I said Bob and Alice are two. One of them is mathematician, one of them is a physicist, and then I will ask the audience who is who. But then I was afraid that people say, oh, but a mathematician can think like a physicist, and a physicist can behave like a mathematician, and then we kind of lost in that thing. So I rephrased it, but the point stands. Can we really tell the difference here between the two? Only by looking at the point of who is it that is considered about many worlds and who is considered about only unique answers and very accurate answers. It is the mathematician, in fact, if you want to hold that criterion, it's the mathematician who cares about the precise unique answer, whereas the physicists are happy with having errors, either in observation or in results. And when the mathematician gets the data from the physicist, they use it to get very similar error margins. Yes?
I don't know that this matters. Yeah, I don't know that this matters at all to what you're saying. I'm not sure I wrap my mind around it completely. But I noticed that for some reason, the mathematicians decided to take the two sides as being, in some sense, more certain than the hypotenuse. I mean, if they could have made another choice, and they would have found that the sides should be somewhere between 0.7 and 1.2 if they'd
would
done
that
the
be
other
the
way
case?
around.
How
In other
would
words,
that be the case?
do just what they did, but they'd start with the hypotenuse measurement in one of the sides and then calculate what the range for the other side could be given Pythagorean's theorem.
But then you have to ask the physicist to do the same. So now we're solving two different problems.
No, but the physicist just measured. I mean, you just said,
yeah. You just measured them. Okay, so your point is if we had A and C and then we want to calculate B instead of A and B and we want to calculate C?
Right. I don't know that it makes any difference for what you're saying, but I don't know why the mathematician decided.
Do you see a difference? In my mind, it's the same. We can flip the problem and then we can still get the point of this exercise is to question whether mathematicians care about infinitely many worlds all the time, and we can imagine whatever we want, and then we can create whatever theory we want, and we can modify it whatever we want. This is the kind of general naive view. Whereas the physicist only cares about one unique situation. In this case, the person, it's kind of clear to me that the person who really cares about the unique answer to the unique situation is the mathematician. Whereas the physicist, between the world that this is 0.9, 0.9, and between the world that this is 1.1, 1.1, there's infinitely many worlds that could be the case. So if you want to hold science to say, oh, science only cares about one universe, I will remind you that that one universe is described within your theory using those observations, using that mathematical language, and that observation is encoded with errors all the time. And since it is encoded in errors all the time, you're getting a collection of worlds that you're dealing with all the time, not only one universe. This is the point.
Right. I mean, but in truth, I mean, this would be very similar to the kind of thing I would have students do in an introductory physics lab. Do something like this, and then see if their measurements if their measurements comport with theory, which in this case would be Pythagoras' theorem, or not, right? See, in other words, whether their measurements are within the tolerances that they estimate their measurements to be within. And so they would proceed to do something like what the mathematician did in this case, but something I think a little more a little better in the fact that they would, for instance, they'd take A and B, square them along with their uncertainties, and see what the range of possibilities for the hypotenuse is. See if their measurement comports with that in the fact in a sense of a sigma thing, right? Did the so they take the difference between the square of the two sides and the difference between the square of the hypotenuse with uncertainties, and see if those two things agree within the propagated uncertainties that are associated with their measurements. And they would find in this case that
I see, I see, I
it
see, I
does
see.
so well. It does
Yeah.
so well that in fact they must have I use this kind of an example to prove to them that they must have overestimated their uncertainties, because the two values agree far too well given the uncertainties that they assign. That's kind of an important thing too. In the case that you've used here, you have clearly assigned far too much uncertainty to the sides and the hypotenuse.
Oh, yeah. I see your point now. I kind of misunderstood earlier. Yeah, absolutely. So there are many ways, and again, this is something I alluded to earlier. There are many ways to deduce that error. There are many ways to make better measurements. Of course, absolutely. If this triangle was under a heat source, you cannot use any physical way except like a measuring tool or a rod or whatever. You have to use lasers. This is the best. So there's different ways of measurement for different situations. And of course, exactly whatever you're saying. And this is an excellent point. I have kind of cheated a little bit by using a very elementary way of calculating here, using a better way of calculating with not taking those steps, but taking different route towards the calculation, could have ended up being a lot closer. That's not exactly to the point, though. The point is going to the many worlds and interpretation versus the very single one unique universe. Whatever you do, right? Even you, and of course in science we can get to +5 standard deviations, +6 standard deviations in measurement. This is 99.9999998 something %. This is incredibly accurate. And when you think of this, they can do this in particle accelerators like the LHC. It's like 5 standard deviations. Do you know how accurate you have to be to get your answer up to 5 standard? This is incredibly accurate. Still, we are talking about technically infinitely many worlds. A sort of. Let me go to the second slide. Maybe this this makes it a little bit easier. So even when we even when we assume that it's not our error. So something kind of Hansen alluded to earlier. It's like we are stupid. Okay, we are stupid, fine. But we kind of know now, and this is a great here link to John's series on quantum mechanics that he did a little bit earlier, like 2 weeks ago, fully on YouTube, hopefully by the end of this week. The Heisenberg uncertainty principle shows that there's an inherent, unfixable, so far, unfixable error in measuring of the physical properties of the particles. I say so far because there's always, every once in a while, a research paper that says exactly what John says. By doing a series of very light, undisturbing measurements, there's a way to reduce the error less than the Heisenberg uncertainty. But then, I don't know. What do I know? I trust the scientific community. I wasn't in the lab with them. I will follow whatever they say. So I don't know. I have no clue. But so far, the established and the accepted thing is that this is unfixable. You can, whatever you do, even if you do a series of very sensitive, very undisturbing light measurements, then you will get to a smaller error, but still an error. So we are locked. It's a property of nature that we will never, as physicists, we will never be able to deal directly with nature itself. John will be happy now. We will never be able to be indirect with nature. This claim that physics only deals with one world, this is just hallucination. You are bound as a physicist to deal with one member, you choose it, of an infinite bounded class of quote unquote toy worlds that are, with double asterisks, coupled, because I've never used that word before, and this is what we will use to talk about meaning and truth and later on, etc. But in some very naive way, those toy worlds that we have are coupled, they are connected with quote